about instance-optimal iterative methods for matrix function approximation. It's not directly an optimization talk, but it'll relate a lot to iterative methods for linear solvers and types of stuff that you guys have probably seen before. So this is joint work with Noah Amsel. He's a student of my brother's at NYU. Tyler Chen, who's a postdoc of my brother's at NYU. He's on the job market this year. And Greenbaum at University of Washington, and my brother, Chris Musco at NYU. All right. So the basic problem we're considering is I have some scalar function f. It maps real values to real values. And I want to apply this to a matrix. What does that mean? If I have a symmetric matrix A, it has some eigendecomposition. The matrix function f of A is just I apply f to each eigenvalue, and I reweight the components of the matrix applying f to each eigenvalue. So another way to think about this, I take my eigendecomposition, and the diagonal eigenvalue matrix, I just entry-wise apply the matrix function f. Okay? I'm only going to talk about symmetric matrices in this entire talk, and symmetric real matrices. What we want to do is we want to compute the matrix vector product f of A times B. Okay, I don't want to compute all of f of A. I just want to multiply f of A times a vector. Understand its action on a vector. Now, for general A, like unless I have a lot of structure, exact computation of this is not really possible, but like very high accuracy computation essentially requires, if I want to just directly compute it, I basically need to do a full eigendecomposition, reweight the eigendecomposition. It takes me something like n cubed or n to the omega time. So what we want to do is we want approximation algorithms that are a lot faster than this. Okay? So that's the problem. Why do I care about this problem? It has tons of applications. The one you guys have probably seen the most is when f of x is 1 over x. Then f of A is just the matrix inverse, and f of A in f of A times B is just the solution to a linear system. Okay, so this is by far the most well-studied version of this problem. Another example would be like, let's say A is PSD, so it has all non-negative eigenvalues, and f is the square root function. Then f of A is just the matrix square root. This is used, for example, if I want to sample from a multivariate Gaussian distribution with covariance A, I would want to multiply this square root times isotropic Gaussian vector. So that'd be one application of the matrix square root, but there's a ton of applications of matrix square root. Another time we care about matrix functions is sort of computing the traces of matrix functions. So the trace of the matrix function f of A is just the sum of its eigenvalues, or in other words, it's the sum of f of the eigenvalues. So for example, if f of x is the log of x, then trace of f of A is just the sum of the logs of the eigenvalues, which is like the log determinant. And this shows up a lot, for example, in like log probabilities and Bayesian optimization, all sorts of places. Okay. Now, this is a little bit different. Computing the trace is different than multiplying the matrix by a vector, but you can estimate the trace just by repeatedly multiplying the function by random vectors. Like this is what Hutchinson's method does. So if I want to do a trace estimation on a matrix function, which I often want to do, the first primitive I look for is, can I at least multiply this function by vectors? All right, that's the problem. Let me just mention some other examples that come up: the matrix sign function, other step functions or spectral windowing functions, the matrix exponential. I already mentioned the matrix square root. But either way, there's a lot of these functions that come up in lots of different applications. So before I move on, any questions about the problem I'm solving or the motivation? Okay, awesome. So how do we approximate matrix functions times vectors? Almost always, people use what are known as Krylov subspace methods. The key idea here is that, let's say f was a degree q polynomial. In this case, I can compute f of A. I can multiply more. It can't really be computed, but I can multiply f of A by a vector using just q matrix vector products with A. And so my runtime, even if A was like totally unstructured and dense, would be something like n squared times q. If A was sparse or structured, it could even be faster. So why can I do this? F of A times B is just like some coefficient times B plus some coefficient times AB, A squared B, etc. So I just compute one matrix vector product to get AB, a second one to get A squared B. I just build up these products, right? So if F was a polynomial, I'd be in good shape. As long as the degree is not too large, I need to do Q matrix vector products with my matrix, which should be pretty fast. So the whole idea of Krylov methods is just approximate general functions with polynomials, and then use this above fact to compute them quickly. That's the whole idea. And they're the main method we have for approximating matrix functions. In this talk, I'm going to focus entirely on a specific Krylov method called the Lanczos method, which I'll tell you what it is in a second. And it can be used to approximate any f of a in some sense optimally, although I'm going to talk about why this sense of optimal is maybe not satisfactory. Just to note, just so you like have a frame of reference, if a was positive semi-definite, if f was 1 over x, this Lanczos method I'm going to discuss gives exactly the same output as the conjugate gradient algorithm. It's a slightly different algorithm. In finite precision, it will behave slightly differently, but they're mathematically equivalent algorithms. Okay. Other examples of Krylov subspace methods you might have heard of that I'm not really going to focus on in this talk. Min-res for solving non-PSD systems, gradient descent, accelerated gradient descent, pretty much almost all non-stochastic iterative methods for solving linear systems can be thought of as Krylov subspace methods. Okay. Okay, so what's the Lanczos method? This is an awesome algorithm. It's really simple. It's used for matrix function approximation, for eigenvalue approximation. It's all over the place. And it has a fairly simple idea. So I'm going to run it for k iterations. It's an iterative method. I'll use k-1 matrix vector products. And what this method will do is it'll compute an orthonormal basis Q that spans the Krylov subspace B, AB, A squared, B, etc. So in other words, the column span of Q is basically all possible degree k or degree k-1 polynomials multiplied by my vector. That's the column span of Q. The method orthogonalizes Q. The Lanczos part of this method orthogonalizes Q via tri-term recurrence. It ensures this sort of nice property, which is that if I look at Q transpose AQ, which is kind of like the projection of A down onto the Q space, this is actually a tridiagonal matrix. Okay? And what we're going to do is we're going to approximate f of AB. So I have A, this big matrix. I want to compute f of AB. I'm going to approximate this as Q. So Q is k by n, where k is the number of iterations, times f of t, where t is this little tridiagonal matrix, times Q transpose. Okay, so that's the whole method. It's kind of totally agnostic to the function you're approximating in the sense that the only place f comes in is you apply f to t. Okay, but other than that, the method's totally generic. Okay, questions on that so far? I'll give you the motivation behind this method in a second. Okay, so like, why are we doing this? I mean, this looks a little bit crazy. What's going on here? Oh, actually, before I say why, I'll just say at least we can do this quickly. So f of t, because t is tridiagonal, you can like compute its eigendecomposition really quickly. So you can compute f of t essentially exactly in k squared time, which the number of iterations will typically be less than your problem size. This would be less than like nk time, where n is the size of the original matrix. So the total runtime of this method is very small. It requires like k matrix vector products with A, and then roughly like k other matrix vector operations. So this second term, like nk, is usually considered lower order. This is just for like adding together vectors at each iteration. Okay, so it's fast, but why are we doing it? The motivation behind this method is that it's exact for polynomials. So what I can observe is that, let's say I take a polynomial, or let's say I just take a monomial a to the I, where I is less than my number of iterations k. A to the I times b is equal to QQ transpose a to the I times b. Because Q spans this Krylov subspace, a to the I times b is in that Krylov subspace. So when I project onto the Krylov subspace, it's a no-op. It's just equal. B is also in the Krylov subspace. It's the first vector. So QQ transpose b is equal to b. So a to the I times b is equal to basically the AI projected on both sides by QQ transpose times b. And this is exactly equal to the Lanczos approximation. This is equal to Q t to the I Q transpose b. That's because t is equal to basically like Q transpose AQ. So if I raise this to the ith power, I get like Q transpose A, Q transpose QA, like a bunch of times. All these middle terms cancel out, and I just get Q transpose A to the I Q. Okay, so this is T to the I. Okay, So for a monomial, this method is exact, okay? And then by linearity, it's actually exact for all polynomials of degree less than k. So if the polynomial is degree less than k and I apply Lanczos to approximate it, it's exact. Okay, so that's sort of the motivation behind this method. Any questions on that? Okay. Now, why is this like cool? Via triangle inequality, you can use this to get a really nice error bound for approximating general matrix functions. So let's just assume for scaling, so because I don't want to write it down, that the L2 norm of B is always 1. So it'll disappear in my equation. If I have a polynomial of degree less than k, I can write the error of Lanczos. So basically my exact matrix function minus the approximation via triangle inequality as the error in applying the polynomial plus the difference between the polynomial and my actual function, right? Oh, I underlined the wrong thing. This is the difference between the polynomial and my actual function, and this is the error in applying. Oh, I said it again, wrong again. Sorry. Sorry. Okay. If I can write basically the error of Lanczos as the error of applying the polynomial plus the difference in my function with the polynomial on my original matrix plus the difference in the approximation for the polynomial and the approximation for my original function. Okay, so there's 3 terms there. But this first term is 0 because there's no error in applying the polynomial, right? So the error of applying a general function is just the difference between that function and the polynomial on A and on my approximation, like on T, basically. B is unit norm. Q is an orthonormal matrix. So this is basically the spectral norm difference between my function applied to A and the polynomial applied to A, plus my function applied to T and the polynomial applied to T. Okay. Or another way to think about it is these matrices have all the same eigenvectors. They just have different eigenvalues. It's basically the maximum over all my eigenvalues of A of the function minus the polynomial, plus the maximum of all the eigenvalues of T of the function minus the polynomial. Or if I want to write this in a nice way, the eigenvalues of T by interlacing are bounded within the range of the eigenvalues of A. So if I want to give it an upper bound on this, this is at most 2 times the maximum difference of my polynomial and my function over my full range of eigenvalues. Okay. This holds for any polynomial P. So if I just optimize over all polynomials, what I get is that the error of Lanczos in approximating this matrix function is at most 2 times the best polynomial for approximating my function over all the values in my eigenvalue range. Or if you want to say it not in math, Lanczos gives within a 2-factor of the best uniform approximation error of F by a polynomial on A's spectral range. This is really nice. Basically, the better F is approximated by a polynomial, the better Lanczos performs. And this is why Lanczos sort of works well for approximating matrix functions. So any questions just about this error guarantee?
Silly question, but is the 2 needed?
Yeah. Wait. No, I don't know if the 2 is needed, actually. I mean, there's examples where this is tight up to a factor of 2. Yeah, I don't know. Good question. Other questions on this? Okay. Let me just remark some things on this. This is a very powerful convergence bound. One thing you could do to use it to show is, for example, like we know that like conjugate gradient or like other like kind of optimal Krylov methods, they can solve linear systems to accuracy epsilon and roughly like square root condition number log 1 over epsilon iterations. This uniform approximation bound would be enough to show that. You just show you can approximate the inverse function with a polynomial degree roughly root condition number. This guarantees robust to round off error. So Lanczos methods are inherently very sensitive to round off error in the sense that if I have round off error, like Q will often be very far from orthonormal, but you can still show that this guarantee holds up to a small factor, which is really nice. And related to Rasmus's question, this is tight up to a factor of 2 for any continuous function f, and for worst case A and B, even when your matrix size is pretty small, even when n is just k plus 1, 1 more than your number of iterations, you can kind of find a worst case B and A that make this absolutely tight, up to a factor 2. Okay, so this is a really cool error bound for Lanczos, but it's often not good enough. This uniform error bound almost always fails to actually capture the performance of Lanczos in practice. If you plot the error that you're getting out of the method, it's usually way, way better than this uniform error bound. I'll show you a picture in a minute. And so this is the entire point of this line of work, is to understand why this error bound is not capturing what's happening in practice and to give better error bounds. And better error bounds are going to require some different notion of optimality because we know this error bound's tight in the worst case. So by better error bounds, I want to look at error bounds that for specific A and B give you better bounds than just the worst case. Okay, so just as an example, yeah.
In the derivations in the previous page, so you're going to bring it back in, right?
Yeah. So note that like this error bound doesn't depend on B, which already tells you it could be kind of loose in some sense. The error bound also doesn't depend on the actual eigenvalues of A. It only depends on the range of eigenvalues, which if people have run like UCG, like you know that the convergence depends a lot on the spectrum, the shape of the spectrum, not just its range. So this is another reason why this is like loose. So just as like an example, Tyler gave some examples of running Lanczos on a bunch of matrix functions like a to the negative 2, exponential, square root. This high line is the uniform error bound. And then there's two lines here that look pretty close to each other. One is what Lanczos actually does. And then one is the optimal approximation in the Krylov subspace, which you get by just computing the matrix function exactly and then projecting it to the Krylov subspace. So this is sort of the best you could hope for, but it's a non-efficient solution. They look like overlapping, but if you plot the relative error here, it's like always pretty small. Like worst case, Lanczos at most, in this case, like 1.5 or 2 times the optimal. So this is the type of behavior we want to explain. Why is Lanczos following this curve rather than that curve?
And what is A here? Gaussian or something?
Yeah, generally the whole thing is rotationally invariant. So like even diagonal A is the same as if you did like random eigenvectors. So A is, I don't remember exactly what he set the spectrum to here. It's probably like a uniform spectrum or like some sort of uniformish spectrum.
But the eigenvectors are...
The eigenvectors are yeah, they don't matter.
They don't matter.
Yeah, so you could think of them as being random, or actually I think these are literally run on diagonal A because then we avoid conditioning. We avoid like round off error. So we usually run it on diagonal when we're doing the test.
Just for the previous slide, so I just want to make sure I got the quantifier. So for any continuous function in K, there exists an A and B such that the error is at least two
yes,
of the
that's
best
exactly it.
okay.
And what you basically do is you exhibit
Thank
we actually proved this this was kind of known for CG, like for solving systems. We just extend this to any continuous function in like our paper. You just basically can solve for this worst case A and B that match this bound. You look at the equal oscillating points of the best polynomial approximation.
Nice.
Other questions? I'm sad, I'm kind of low on time. I know I'm gonna run out of time, but we'll get through as much as we can. And please ask questions because I don't really want to rush. So what do we want to show? We want to prove instance optimality bounds. We want to show that for like common matrix functions F, that we have a bound, which is basically that Lanczos, the output of Lanczos, is within some approximation factor C of the best possible output, which means the best degree K polynomial for approximating our function when applied to B. So here we're taking into account A and B, not just the spectral range of A. And another way to think about this would be the same as, this dotted line here. This is basically the error you get from exactly computing the matrix function and projecting it to your Krylov subspace, which is inefficient. Okay. This type of instance optimality guarantee, if you ignored the C, which will be relevant obviously, is always at most the uniform approximation bound, but it's often smaller by a wide margin, as we can see from like these previous plots. It's usually much, much smaller. Now, in the linear system case, people might already know that CG outputs something that is optimal, just not in the 2 norm, but actually in the A norm, like the energy norm. So if you just convert it to the 2 norm, this is known to hold for f of x being 1 over x, where C is square root of the condition number. Or it holds for C equals 1 in the A norm, is how people usually think about it. There's some like partial guarantees for the matrix exponential shown by Drushkin, Greenbaum, and Knischman. But I'm not going to write them down because they're kind of messy, but they're kind of getting at some sort of instance optimality guarantee. But prior to our work, we weren't really aware of any other known results for really important functions like matrix sign functions, square root, etc. So the whole goal of our line of work is to basically prove these types of bounds for other important matrix functions other than just the inverse. And my goal of giving this talk is to convince you to try to prove these things. We make some really minor progress, basically. We show really bad bounds for rational functions, which is like a slight extension of 1 over x. I would like you to show better bounds for broader classes of functions, basically. So what is our result? I mean, I don't mean to trash our result. It actually gives us something nice, but let's just state what it is. I have a rational function. It's a degree mq rational function. So it's a degree m polynomial p on top of a degree q polynomial. In the poles of this rational function, meaning the roots of the stuff in the denominator, which is basically where the function could blow up to infinity, the poles are going to lie outside of my eigenvalue range. This kind of makes sense. Like if I have poles in my eigenvalue range, bad things could happen. My function could go to infinity on my eigenvalues, and I'm not going to get any good approximation. Although, if I have time, I will mention we have some results when poles are in the eigenvalue range. An example of poles being in the eigenvalue range, a really simple example, is the function 1 over x when your matrix is not PSD, right? Your eigenvalue range includes 0, but the function goes to infinity at 0. And there's actually some really cool connections that you can get between rational functions and solving non-PSD systems with things like min-res. So I'll talk about that hopefully at the end. I'm going to define AI to be just A shifted by my ith pole. Okay. What we show is that Lanczos is instance optimal for such a rational function where my approximation factor is basically q, that's my number of poles or the degree of the denominator, times the product of the condition numbers of these shifted a's. Okay. Now, there's a slight caveat. Specifically, k needs to be bigger than m, the max of m and q minus 1. So it needs to be bigger than the maximum of the degree on the top and the degree on the bottom. This is a really mild condition because usually m and q minus 1 we're thinking of as relatively small constants. So the number of iterations will almost always be bigger than this, right? The second other small caveat is we don't actually compete with the best approximation. We compete with the best approximation of a slightly lower degree. So it's kind of like a bicriteria approximation. So we compete with the best degree k minus q plus 1 approximation. Again, it's pretty mild. If you're running 100 iterations and q is 5, you're competing with the best 95 or 96 iteration algorithm. So it's pretty mild, but it is a slight relaxation of what we wanted to show. Any questions just on the theorem?
Just wanted to check. So this implies something for general functions too by first approximating with a rational function? Or?
Yeah, I'll say that on the next slide. I'm not going to write anything formal down, but yeah, why do we care about rational? Well, actually, wait, any other questions before I move on to sort of some remarks on this? Okay, yeah, let me make some remarks on this. So why do we care about rational functions? They're interesting in their own right. They can include 1 over x. And like for 1 over x, this will match up to some small like tweaks. It will kind of give you the instance optimality of CG. It will be slightly worse than the naive proof. But it also includes things like 1 over x squared. This was the first function we looked at. We were like, we know that Lanczos is optimal for 1 over x. Is it optimal for 1 over x squared? Like, it's really not that big of an extension. So it includes those types of really simple functions. So this is one motivation for looking at rational functions. Another important motivation for looking at rational functions is that they often give really accurate approximations to functions that have discontinuities much better than like polynomials do. So this includes functions like square root or step functions and stuff have really good rational approximates. So I'm not going to write anything down in this talk, but you can use our error bound to give stronger error bounds for Lanczos and approximating functions that can be approximated with rational functions via some sort of triangle inequality type argument. So exactly what you're saying. Something to note is that our approximation factor C is really bad. Notably, it scales exponentially in Q. So even if all your poles were at 0, our approximating factor is like Q kappa to the Q. Okay. We think this can be improved. The best empirical lower bound, we have no theoretical lower bounds, but we have simulations showing that we can make the approximation factor as bad as square root of Q kappa. But I mean, there's a big gap there. So we couldn't make it grow exponentially in Q. So this is a question. Can you get our error bound to be better? Even with our bad error bound, the error bound gets much closer to approximating, explaining the behavior of Lanczos than the uniform bound does. So in some sense, these plots are kind of silly. Like this is the optimal bound and this is R bound. And since it's a log plot, R bound is just shifted up by whatever C is. But you can see that R bound is much, much less than the uniform error bound in many reasonable circumstances. So even though we have a pretty bad error bound, it's often much tighter than the uniform error bound. Okay? But it could be tightened, which I think would be nice direction for future work. This is for rational functions. These are all for rational functions. The second two rational functions are rational approximates to the exponential and the log, because these are the types of things that show up in practice. On this slide, I'm not going to talk about these in the talk, but as Kevin was asking, we derive error bounds for things that are well approximated rational functions. So I'm plotting some of our error bounds for square root and inverse square root versus what was previously known the uniform error bounds, and they're also tighter. So this is another reason to care about rational functions. Okay. All right, so let's see. I have like 2 minutes left. Let me try to sketch the proof really quickly. So what I'm going to first do is just sketch, and if I only get through this, it's fine. Just going to sketch the proof for why is Lanczos optimal for f of x being 1 over x. This is where we start from trying to prove that it's optimal for rational functions. Okay. So people may have seen this before. Basically, if I look at the difference between the actual solution to the linear system and the Lanczos approximation, if I multiply through by like a to the 1/2, I basically can upper bound this by square root of lambda max of a. That's from multiplying by a to the 1/2 times like the whole thing, where I now have a to the negative 1/2 be a to the 1/2 times the approximation. And what I can do is I can just expand out T as Q transpose AQ. And then I can write B as a to the 1/2, a to the negative 1/2 B. And the magical thing here is that this operator sitting here is just the L2 projector of a to the negative 1/2 B onto a to the 1/2 Q. So this here is actually an optimal solution to a linear regression problem. I can write this as basically the min of basically a to the 1/2 Q times x minus like a to the negative 1/2 B. This is an A norm projection onto the Krylov subspace, but I didn't want to really use the A norm. If I just multiply through again by a to the negative 1/2, I lose this 1 over square root of lambda min, but I get the actual best approximation to my system in the Krylov subspace, which is what I wanted. And so basically this is exactly the same as an instance optimal guarantee where the prefactor is like square root of kappa. Okay. If you've seen this before, how this is usually worded is that Lanczos computes the A norm optimal approximation of A inverse B in the Krylov subspace. A norm and 2 norm are equivalent up to a square root of kappa factor, and this gives this directly. Okay. Now the main idea on how to generalize the rational functions is really everything. Just once you can do 1 over x squared, you can do a lot of messy algebra and do all of these other rational functions. So I'm only going to look at 1 over x squared. Here we use triangle inequality. We look at the error of Lanczos. We split it into 2 different errors. One is the error of the exact matrix function minus this funny thing, which would be like if I applied Lanczos to do one of my inverses, but then I exactly applied the other inverse. And then here is basically if I just apply Lanczos to do both inverses versus if I apply Lanczos to do one inverse versus exactly applying the other one. So I just split it this way. The first term, you can show via the same argument as on the previous slide that this is actually the best approximation to A negative 2B in the span of the Krylov subspace in the A norm. And so following what I just did on the previous slide, this is basically within opt up to a square root of kappa factor. Okay, so this term is kind of easy. The second term is a little bit more funny. First, what I can do is I can pull out a Q T negative 1Q. So I do that, and then I have this approximation term here. The spectral norm of Q T negative 1Q is at most like 1 over lambda min. And then this term here, that's just the Lanczos approximation to the inverse. So this is at most like square root of kappa times the best approximation to the inverse. But that's not what I wanted. I wanted the best approximation to 1 over x squared, not to the inverse. The key idea is that the optimal error for approximating the inverse with degree k can be bounded by the optimal error for approximating a negative 2 with degree k minus 1. Because if I had some good approximation to a negative 2, I could just multiply it by a and I get a good approximation of the inverse. There's no way that approximating a negative 2 is significantly easier than approximating a negative 1 because I can derive an approximation of the inverse from the other. So basically, like, I don't have time to do the actual math, but I relate this opt to my actual opt and lose like a lambda max factor when I do that. And overall, this gives like some kappa to the 3/2 factor times actual opt. So I'm like over time, so I'll just conclude. Basically, this is the analysis. I just add these two things together, and in the case of a negative 2, I get like 2 kappa to the 3/2 times my actual opt. The key idea was just relating the optimal approximation to the inverse with the optimal approximation to a negative 2. Okay, so I'll just conclude with some open questions. First open question is tighten our bounds or show stronger or lower bounds. So as I mentioned, our numerical lower bounds, which we haven't proven, are way far away from our theoretical upper bounds. It would be cool to extend our results to the case when the function has poles in the spectral range. In this case, Lanczos seems to oscillate between very bad and near optimal solutions. And not only does it seem to, it definitely must do this. But we can actually explain this in the case of 1 over x. So if we can actually relate the convergence of conjugate gradient to the mid-res algorithm and show that this oscillatory behavior is necessary, but that you always oscillate to a good solution. And it would be really cool to show this for general rational functions. Proving instance optimality of matrix exponential, which would extend the work of Drushkin et al. Proving instance optimality bounds for matrix square root, et cetera. There's a lot of sort of open questions here. And then the final thing is understanding the role of finite precision. So we know that finite precision matters a lot here. For conjugate gradient, this instance optimal bound is completely dependent on your precision. And we have very little understanding. We don't even have a lot of understanding of the conjugate gradient case, to be honest. So anyways, doing anything with finite precision would be really interesting. So that's it. Thanks for your time.
I think so that we have a little break, we should take questions offline. But we have another exciting discussion session coming up at 15:15. And this time we'll hear from Sigrid and Linyu. So
Can I ask you?
Yeah.
Do you have to like Tom Johnson